Welcome back, folks. In this video, we are going to spend some time talking about velocity time graphs and what those show. Remember, one of your big goals for this course is to be able to take graphs and turn them into a story. We've done that a little bit with position time graphs, and today we're going to spend a little bit more time talking about what velocity time graphs show. So what I'd like to do to start is compare a couple of graphs that are actually going to be exactly the same. The only difference is how we've labeled the y-axis. So we've got a position time graph here. We've chatted previously and we talked about how those graphs show velocity. But what if we switch up the dt graph and we make it a velocity time graph? Now what is that showing? And it turns out you can actually do just a quick little switcheroo of a word. Here, these lines are showing that the velocity is increasing as time goes by. We would say that's an acceleration. So really all this story is telling us is all about acceleration. And you're going to find there's a trend as we go through the notes here for the first few minutes that displacement time graphs are really good at telling us about velocity. Velocity time graphs are very useful to tell us about accelerations. So the steeper the line, the bigger the velocity on a displacement time graph. The steeper the line, the larger the acceleration if it's a velocity time graph. If you want to actually get a number for the velocity on a position or displacement time graph, then you would simply take the slope of the line. And what if you actually wanted an acceleration off a velocity time graph? You simply find the slope of the line. Again, notice we are just swapping the word velocity for the word acceleration. Recall that straight lines tell us not only that an object is moving with a velocity, but with a constant velocity. And you're critical thinkers, I bet you know what's coming next. Straight lines on a velocity time graph show a constant acceleration. In this case, constantly gaining some velocity, and the blue line is constantly gaining less velocity, a smaller acceleration. Now, that's not the only lines that you'll see on these two graphs. What about the mighty horizontal line? So on a position time graph, on a dt graph, that horizontal line tells us that the object is not moving. While on a velocity time graph, I like to say that the thing is cruising. It's locked in at some specific velocity, and you would just go look at your scale to see exactly what that is. Another way to think about this, if you want to play that, hey, let's switch the word game, let's switch velocity to acceleration, is that horizontal lines on a position time graph show us that the object has zero velocity, while a horizontal line on a velocity time graph tells us that the object has zero acceleration. So cruising means zero acceleration, not moving means zero velocity. Same thing. Now, one other sort of set of lines we'll see on dt and vt graphs are the curvy ones. And you may recall again from previous lessons that on a position time graph, it doesn't really make sense to talk about the slope because the slope is changing, but we can find an average slope. That's a secant line. That would give us the average velocity for an object over some given time interval. If we take the average slope of the same segment on a velocity time graph, switch the word, we get average acceleration. We also talked about tangent lines and how a tangent slope gives us the velocity at one instant, the instantaneous velocity. How fast are you going right now? While if we do exactly the same thing on a velocity time graph, the tangent slope gives us an instant acceleration. Again, switching the word velocity for the word acceleration. Easy stuff. We're going to skip that for now. This you can scribble down in your notes. I want to talk about what to do with ticker tape data. And we've actually played this game before already. We did this with velocity. We saw that there was a quick and easy calculation here that actually turned out to be a whole bunch of little slope triangles. But we didn't think about it like slope triangles. You may remember that to calculate velocities, we simply took d2 minus d1 and divided by delta t, the time interval. For example, if we are looking at this box right here, just to put some numbers on the page, remember d2 means not the bigger number necessarily, just the number on the right-hand side. We're straddling these two values right here, the 224 and the 0.96. So it's the number on the right, 2.24. Sorry, my screen moved a little bit there. Minus 0.96, all divided by. Now sometimes students get confused because this box is actually straddling two time values, and they get stuck. They go, do we use 0.6 or do we use 0.4? And the answer is you actually don't use either of those. We want delta t, the change in time. And you can see on this table that as we jump from one time value to the next, we're going up by 0.2. So your delta t for every calculation is simply a 0.2. And just to save some time, I am simply going to page down because I think I've got the values in here already. There you go. That ends up being a 6.4 meters per second. And if you go and you play that game for the rest of them, here they are. Pretty straightforward. Something a little wonky here. We actually lost some velocity. That's okay. Don't sweat it. So that's that row all filled in. Now to find acceleration, it is also pretty darn straightforward. It's actually an equation I haven't showed you yet, but I kind of have. And you're critical thinkers. I bet there's a few of you watching this and you know what's going on. Well, Mr. Heinrich, I think I know what you mean. You've said we've kind of seen this. If I want to find an acceleration like this one right here, maybe it's simply v2 minus v1 all over delta t. And you're exactly right. Well done. So for example, just to put some numbers on the page, 6.4. v2 is just the number on the right-hand side minus the number on the left-hand side. Divide by delta t, which we already said. We're ticking up by 0.2 seconds every time. It simply looks like that. And again, just to speed things along, I've got all those values in there. Whoops, I did that one first. Whoa, there it is. 14 would have been the answer to the one that we wrote down. Equals 14 meters per second squared. So pretty darn easy couple of calculations. They really are one and the same. One other quick note, if I scroll back, I should put this in here. Remember that when we calculate velocity, I think that was 6.4. When we calculate all of our velocities and then we go to plot them on the page, remember we have to plot on the in-between times. So we've staggered that row by half of a box to remind ourselves that this velocity of 6.4 meters per second doesn't actually get plotted on 0.4, doesn't actually get plotted on 0.6. It actually gets plotted straight down the middle on 0.5. So in this case, you would plot data points on 0.1, 0.3, 0.5, 0.7, and so on. You'll see the acceleration row is actually staggered by another half of a box, and it actually falls in line with the rest of the values, or the time value. So 14 meters per second squared, if you had to plot that data point, you'd actually plot it at 0.4. And if you had to plot the 18, you'd actually plot on 0.6. So it's actually only the velocity time graph that's a little bit wonky. So the last thing for this lesson is converting between position time graphs, velocity time graphs. We've done that conversion. Now we're going to throw in an acceleration time graph into the mix. Turns out it's pretty darn easy. Again, you've kind of seen this before, even though you haven't really yet. Do recall that in order to convert from a position time graph to a velocity time graph, so maybe I should get these arrows out of here, sorry. We'll draw a couple sets of arrows. We talked about this in a previous lesson, that to get from position time to velocity time, we measure the slope of the lines. Well, it turns out in order to get from a velocity time graph to an acceleration time graph, hopefully you know this because we've talked about it, how do you actually get acceleration off of a velocity time graph? You simply measure slope. So it's really nice. The rules of the game, exactly the same. And we also talked about how to go from a velocity time graph to a position time graph. It's all about measuring area. Got a bunch of little rectangles and triangles. And it turns out that rule is exactly the same to get from an acceleration time graph to a velocity time graph. We still measure area. So the rules we learned in an earlier lesson, they are just the same rules that we're going to use again today. So what we can do is we can actually look at worksheet 4. That's a great one to practice this skill. So worksheet 4 looks like this. We've got a chunk of a velocity time graph here in the middle. We're going to have to convert both ways, back up into position time graph data, down into acceleration time graph data. So I like to always remind myself of the rules of the game. I measure slope to get from position to velocity, and slope to get from velocity to acceleration. And then when I'm going the other way, when I'm working upwards, if you want to call it that, it's all about measuring area. So nice to have these little reminders. Now let's go ahead and talk about maybe the slopes first, because I think that's probably the easiest. So what we're going to need to do is figure out the slope of a couple of line segments here. Shouldn't be too bad at all. Let's go from there to there, 0 seconds to 1 second. What is the slope of that line? Well, it's horizontal. It's got a slope of 0. What is the object doing in that 1 second time interval? Well, I can see from that velocity time graph that it's cruising. It's just cruising along at 10 meters per second. That means it has no acceleration. So the slope of 0 means on the acceleration time graph, we are going to show that the thing has no acceleration for the first second. I do want you to go and draw a line over that x-axis, even if it might be a little bit hard to see. Humor me and do it anyway. Now going back to the next line segment, which starts at 1 second and ends at 2 seconds, what kind of slope have we got? Well, that's easy. It's another 0 slope. But if you look at it now, this object has gone from 10 meters per second cruising to negative 20. It's now cruising to the left at 20 meters per second, but that's still not accelerating, right? It's just cruising. So another line right along the x-axis at 0, showing no acceleration. Now, from 2 to 3 seconds, yay, we finally have a slope to calculate. This is good. Otherwise we get bored. From 2 to 3 seconds, we go from negative 20 all the way up to positive 30. That's a rise of 50 meters per second, and that takes 1 second. So that's a slope of 50. So that means from 2 to 3 seconds, this object now has a huge rate of acceleration, 50 meters per second squared, even faster than those top fuel dragsters. So I'm going to draw a nice flat line showing that, hey, we've got some acceleration at 50 meters per second squared. Now, that's all we can do with slope. That's not too bad. Let's play the area game. This one's a little bit tougher, but I still think you'll be just fine. What we want to do is find the area of some rectangles and some triangles. The first area we're looking at, we're going to turn some velocity data into position data. It's going to be that rectangle right there. So area is simply length times width, or base times height, however you learned it in math class. And here we know the area is positive because this rectangle is above the x-axis. So if you're trying to determine positive versus negative areas, it's simply, are we sitting above the x-axis? That's positive. Or below the x-axis? That's negative. So here we're worth 10 high by 1 second. So that's an area of positive 10. Now recall, that doesn't necessarily mean that we go to positive 10 on the position time graph. That means from wherever we left off last, we are going up 10 meters. So if I go up to my position time graph, well, I guess you can see here we did start at 0. So I need to go up 10 meters by 1 second. It's going to put us right there. Now, maybe the tricky part of this process is, how do you join those points? What does that look like? Well, we talked about how this thing had no slope because it was cruising. What does a constant velocity or cruise look like on a position time graph? Well, that looks like a time to grab your ruler and draw a nice straight line. So that straight line there shows a constant velocity for the first second. Now what we've got going on with some areas is there's actually two shapes here that we have to break apart. There's a rectangle sitting below the x-axis and a little triangle sitting below the x-axis. So let's start with the little rectangle. We'll divvy this thing up into a couple of shapes. I want to find that area right there. Again, it's in negative land, right? It's below the x-axis. So that's going to be a negative area. So it drops 20 in a time of 1 second, which is an area of negative 20. This is where some students will go, Mr. Heinrich, you screwed up the position time graph. I can't go to negative 20. It's not even on there according to your scale. Well, remember that doesn't mean go to negative 20. That means from wherever we left off last, you're going to go down 20 meters in the next 1 second. So we were sitting at 10 meters, so that means by 2 seconds, put a little mark for myself, we need to drop all the way down to negative 10. We go down 20. And remember, what kind of line do we draw? Well, right here, this zero slope means the thing was cruising to the left at negative 20 meters per second. That means grab your ruler, play connect the dots. Always kind of fun. Straight line. Okay, now we've got a little triangle in here. We want to find this area. And a really common mistake here, students will call this a positive area because they see the positive slope. But remember, we are not concerned about slope right now. We are simply looking at area. And it's still below the x-axis. It is in negative land. So this one is worth negative 20 tall by 0.4 seconds across. So negative 20 times 0.4 is negative 8. Divide by 2, base times height divided by 2 for a triangle. That is negative 4. Which doesn't mean go to negative 4. That means from wherever we left off last, we go down another 4. And that has to happen by 2.4 seconds. So I'm going to make a little note for myself. There's 2.4. We need to be 4 meters below where we left off on the DT graph. It's going to take us right to the bottom. Right there. Now, the tricky part for students is how do we play connect the dots? Is it a straight line? Is it a curved line? Well, in this case, now you do look at the slope and we say this is a positive slope. Another way to think about a positive slope is that the object has a positive acceleration. If we turn that into sort of normal speak, we would say the object is speeding up. And speeding up, remember, means that a line curves up. So that's like a smiley face. It's going to be some part of an upward curve. That's what speeding up looks like. Now, I guess in this case, the best we can do, we can't really be going on our way up, but we're trying to go up. It's going to look something like that. The line is starting to bend upwards. Now, we've got this positive slope that's going to continue, so don't be surprised if we continue that nice upward bend. But before we do that, we've got one more triangle here, this time sitting in positive land, right, sitting above the x-axis. Let's find the area of that one. Positive something. It's worth 0.6 seconds across the base. It is 30 meters per second tall. 30 times 0.6 is 18. Divide by 2 is positive 9, I believe. So that doesn't mean go to positive 9. That means from wherever we left off last, let's go up 9. And that has to happen by 3 seconds. So right now we're at negative 14, so that's going to take us up to negative 5. Right there. And we have to figure out how to join those 2 points. In this case, we still have an object that's accelerating, also known as speeding up. So we are going to continue the upward curve. Something like that. You want to make sure that you use your ruler for straight lines, and that way I can tell them apart from curved lines. Now, the last little piece is this rectangle here at the bottom to drop all the way down to our acceleration time graph. We'll find the area of this rectangle in here. Now, this is a negative area because it's below the x-axis. We're in negative land, and it is negative 30 by 1 second. So that has an area of negative 30. And don't play the game where you think, oh geez, Heinrich, you screwed up the scale again. The VT graph doesn't go to negative 30. Well, that doesn't mean go to negative 30. That means go down 30 from wherever we left off last. And you can see here we're sitting at a positive 30. So we're actually just going to drop right down to 0, and that happens by 4 seconds. So we need to get to there. What kind of line? Well, here this horizontal line tells us that we have a constant acceleration. We're locked in at negative 30 meters per second per second. What does a constant acceleration look like on a velocity time graph? It looks like a ruler straight line. So grab your ruler, play connect the dots. Now, one more triangle to find here. This is another one where sometimes students, they get a little bit mixed up, and they look and they see the negative slope and they think, oh, that's a negative area. But it's not, right? The area, it's sitting above the x-axis. This is still a positive area. It's 1 second long by 30 meters per second tall. Divide by 2 because it's a triangle. That is plus 15. That doesn't tell us to go to positive 15. That tells us to go up 15 from wherever we left off last. And it looks like we left off at negative 5. So by 4 seconds, we need to be 15 meters above that. That's going to take us to 10. And how do we join those 2 points? Well, here, if we look, we've got a negative slope from 3 to 4 seconds on our velocity time graph. That means this thing is slowing down, decelerating, negative acceleration. I like to think about it maybe as slowing down, because when something is slowing down, then your position time graph is going to be curved down, kind of like a frown. Woo, rhyming skills. So it's going to be some kind of that curve, and really we're looking at just the first half here. We have this thing starting to curve downwards, something like that. So that's your conversions between position time, velocity time, and acceleration time graphs. We'll chat more about this in class or in a Zoom meeting if we're online by this point. You don't really have any homework. We just did the homework together, although there will be some extra practice coming at you soon. So hang on to that thought.